My name is Kyle Pazandak, and I'm an information security engineer at Jamf that does a lot of code development, code review, application, and vendor security reviews to help decide which software and vendors will best run in our environment to meet some of our security and compliance goals. I'm joined by Bryson Tyrrell from our DevOps section. He leads a lot of our code deployments and a lot of DevOps workflows. And we're going to talk today about some of the things that we look for in secure application development and secure code deployment. We're limited in this talk to about 20-30 minutes of each of these. And each of these slides could easily be 1 or 2 hours long discussions in and of themselves. So please take what we're going to talk about with a grain of salt instead of being as fact. Bryson and I will talk a little bit about what we look for in raw code, how we write something that is generally considered to be secure and compliant to standards, and how we take these code bases and build them into deployment packages to abstract away many of the security and compliance requirements while also keeping the services generally up to date. So we're going to talk a bit about secret storage, encryption, authentication, authorization, and accounting, often called AAA, logging, and deployment paradigms that we tend to use. But before we get into this next slide, I want to talk about a little anecdote. Every 3 to 3.5 years, the amount of people that define their daily work as developing code doubles, which means that anytime that you go into our industry, a full half of the industry has less than 5 years of experience. No other traditional employment vertical has this problem, where there's a severe shortage of experience, and some things can only really be taught by experience. So please take this with a bit of grain of salt. The first slide that could easily turn into our discussion is encryption. Encryption is a protection against non-repudiation attacks, or basically you want to ensure that you're talking to the right person and that what they're presenting to you is the correct information. It kind of generally falls into two overarching stories. The first one is at rest. And when I mean at rest, I mean data that is statically present on your computer, not rest as in the API framework that a lot of us work with. And then the other concept is data in flight. In flight may refer to on the network wire, in with a TCP or UDP connection, or the data that's being combined together and sent over an HTTPS channel. When it comes to talking about encryption, though, you really want to talk about having to think about who has access and how they have access, and of course, the logging in AAA. Ultimately, you need a way to grant the who the method of how. And this can be done a myriad of ways, but the most common that I want to talk about is generally secret storage, because ultimately, your encryption methods are actually just secrets. Almost every script, program, integration, user account, or whatever has some form of secret that needs to be shared. These can be used to authenticate and or authorize a user to a corporation, an integration to a web service. It can decrypt a data store. These types of secrets are vast, and their formats are extremely varied. They range from basic authentication of just a username and password to certificates, short-lived authentication or authorization tokens. There's thousands of services that constantly browse GitHub and other public repos to find accidental exposures of these. The goal is to, in a way that is secure, allow your user, your service to function with another user or service. And some of the most common ways that you'll see are kind of listed here. For scripts, you may deploy an encrypted file that has your secrets in it, or they're just encrypted in a field that's within the JSON or plist, and then your application has a way to decrypt just that field or the document as a whole, or it might be able to fetch a method to decrypt what is in there. It's also common if you work in Python to store these as OS environmental variables, and you can break the connection between a script running and the credentials deploying to the machine. If you are deploying this as a web service or web app, you may be able to use things like stage variables or deployment variables that, again, the intended purpose is to take your secrets and remove them from your code, but to deploy them with your code such that your code doesn't necessarily store them statically with it. Deployment template variables can be used to remove secrets from the service and instead have them deployed at the time of deployment. This is a pretty common structure. Then you also have common third-party ones, such as AWS KMS, that are just abstractions of your secret storage. You can't talk about encryption without going into the network. And as a former network nerd myself, this is an area that I think needs some kind of addressing in application development. Understanding outside of your application when and where your system encrypts data and system resources is important. When we look at it from the network layer, there are traditionally 7 total layers that we talk about, with the 7th layer being your application, your integration, or your script. Think of this as the top of Maslow's hierarchy, so to speak. However, you probably have often heard about level 2, level 3, or level 4, or layer 2, layer 3, layer 4, which are the data link, network, and transport layers, respectively. These 3 major steps are the steps that you have to walk through to open a session for your application to work with a remote service, regardless if it's TCP, UDP, HTTP, or HTTPS that ride on top of those protocols. A packet or set of packets that leave your devices to a requested service must go through the network stack. And once it's on the stack, it goes to a router. And once it goes to the router, it goes to a gateway. And once it gets to the gateway, it talks to the internet over what's called BGP. At each layer, encryption occurs. For instance, in layer 2, the packet is checksummed. After it is converted to a layer 3 packet, the internal body is actually encrypted after a SYNAC agreement, where it uses an encryption method that would be analogous to how you do RAID technologies. And then once you have all of those together, the body of the entirety of the package is encrypted with SSL or TLS, but more on that later. It really is a marvel at how this all magically just works, and it blows my mind that the internet even sometimes functions, considering how perfectly it has to fit together on a day-to-day basis. But long story short, if the layer 2 is broken, you can't talk to a router. If the layer 3 is broken, your router can't talk to a gateway. If the layer 4 is broken, your gateway can't talk to the world. And if your document layer is broken, then your device and the foreign host can talk, but they can't agree on how to talk to each other. And this is often called the presentation layer. When it comes to the presentation layer, this is where you often see most of our network problems, which is certificate-based encryption on top of TCP, which is used to encrypt the data stream and the document between the 2 devices on the layer 7 services. When it comes to HTTPS, a protocol, and its methods of encryption, you have a few gotchas. The first is there are so many scripts out there that use curl-k, or from the Python world, use request verify equals false, where you ignore the entirety of the certificate-based encryption process. These are bad habits, so please don't do it. It's actually something that I passively look for in pretty much everything that we run in our entire environment. If the cert is self-signed, as in the entity that is issuing the cert and the CA isn't publicly accepted or widely distributed, trust the cert. Don't ignore verifying the cert. Or buy a cert from a public domain. These are basically just companies that many devices have agreed to that should be trusted. You pay them to host a cert. Your device, in part of that communication, verifies aspects of the certificate that is ultimately used for encryption. And this way, you have your own private keys and public keys servers. So I'm going to talk about how this all generally works on the next slide. This is how a device starts a TCP and HTTPS connection. This can also explain why there are so many cases of, I have a 1 gig connection, they have a 1 gig connection, why can we only transfer at 30 megabytes between each other? At about 40 milliseconds of round trip time, you should have only about 30% of line capacity in your throughput. It takes a minimum of 4 round trips on a single TCP stream to open up a connection that is considered secure. You're basically exchanging secrets back and forth, and after the 4th one, you exchange a set of symmetric encryption keys that allow you to communicate for a set number of TCP packets. And then once you get through that set number of TCP packets, you have to redo this. So it's common to have to redo this entire 4-packet handshake, or 3-way handshake as it's often called. Have to redo this every 1,000 packets or every 1,500 packets. TCP will actually auto-negotiate how many packets you are allowed to send on a single set before you have to redo this entire process. The best part of Jamf Cloud, though, this is all magically taken care of. All of our certificates that are deployed in a standard Jamf Cloud or premium that's run in a standard fashion are maintained by us, so you don't need to worry about certificates expiring in Jamf Cloud. Logging. While we talk about TCP and its encryption, failure to communicate is one of the most common issues in applications. Either a cert failed, the web service, Jamf, or device are not reachable. These are some of the most common things you need to log and figure out your error handling and recovery from. So many applications have a chain of 1,000 plus API calls and no error handling about just one of them, so that if a single API call fails, the entire workflow fails. We need to consider first logging, and second, when you can raise an exception and when that exception can be handled, ignored, or recovered from properly. But first, logging. The best time to build logging into your service is when you first build it. The second best time is, well, now. While Jamf isn't exactly the best in the world when it comes to producing logs in this format, you should use a structured format such as CSV, JSON, or XML. Often these are now getting sent to a SIM platform, whether that's a cloud native or some third-party service like SIM service like Splunk. A consistent industry logging structure will go a long way, and it will give you a balance between giving enough information but not enough. Also, be careful about what you put into your logs when something happens to fail, because you don't want to accidentally dump PII, GDPR, or other company sensitive information such as secrets directly into your logging platform. So don't log what your key was or what your short-term token was into the logging platform. I would just like to say that when Log4j came out, I was not vulnerable to it because I only print my errors. All right, so here's an example code block of some of the things that I would take a look at. I tried to get through this without showing any code because code becomes rather dated rather quickly. But this is a very basic workflow that you would have in Python. Basically, this is going to call a computer from a Jamf Pro. And I'm going to highlight a couple of areas that if I saw this code block come into our development area, that I would kick it back to the user. The very first one, the URL, username, and the password are all hard-coded in here. You need to find a way that is agreeable between the security and compliance structure and the code developer and the services on how to abstract that. Another one that you want to be careful about is your try except blocks. When you are calling a Jamf Pro and you have to go first get an authentication token and then use that to then go get your device, you need to consider how you're going to handle errors. Like in the case of you have a bad username and password in getting your auth, or it has expired, or the computer no longer exists when you thought it should exist. You should raise these. Raise is a fancy way in Python to be able to raise an exception and tell something that is calling that function that there was some kind of error that came with it. And you don't always have to use a try block to catch a raise. So like, for instance, if you're searching a dictionary, you can use if a key is in the dictionary. If it's not in the dictionary, you can use a raise function. And then when you find an error, you need to decide if it's possible that you can recover from it, or when you need to revert back to a previous state or prevent the script from running further. But after this, I'll be joined. After this, assuming that we got this all happy and we're good with this code, I'm going to be joined by Bryson to talk about how we would turn this into a CICD pipeline and deploy this into our environment.
All right. Hey, everyone. Kyle said I'm in DevOps, so Kyle needs to put $1 in the swear jar after this. I'm actually a member of one of our platform teams, but the platform teams here all practice DevOps or implement DevOps practices. DevOps practices. And I'm actually going to talk to you a little bit about that here. I actually clicked forward one too many. The biggest one is going to be what Kyle just mentioned, CICD. And I'm going to walk you through what these mean. There's actually a third one that's not shown in that little acronym. So continuous integration. Continuous integration is the practice of code changes are merged frequently into a central location, and it triggers builds and tests. You are continuously testing and evaluating your code. I'll talk more about this in a little bit. The next facet of this would be continuous delivery, where you have a almost fully automated release process where you can deploy your code changes at any time, which is a little different from the third one, which is continuous deployment, where every single change passes all stages of your pipeline and is released with absolutely no human intervention, and only a failed test will prevent deployment. This is the one that my team generally tries to strive towards. This one is what allows us to ship fastest and also the most secure. All right. So one thing I'm going to touch on here, which is an earlier part of the CI/CD process, is going to be the supply chain. And Kyle mentioned at the beginning of this, every section of this could be its own hour-long talk. It's a really complex subject. We can't really get into all the possible details of it. The one approaches to any one of these three topics that you see here: securing access, securing code, securing systems. you might vary depending upon the tools and the software stack that you use or what's available at your organization. So I'm not going to get super detailed here, but we are going to focus in on securing code. This is something that seems to be popping up in the news a lot more often lately, especially with attacks on popular packages in various languages and ecosystems. Security vulnerabilities in your dependencies, you need to address them before there's a chance where they could be exploited in running environments. Some of these attacks on package repositories have resulted in malicious code attempting to steal sensitive data, intercept access credentials that are exposed in your environment, or even access credentials that are being referenced off disk. You even have malicious packages running Bitcoin miners or other crypto miners in whatever resources that they have available once they get imported. Some of the security scanning tools that are out there that try to address this, where they scan your code base, look at the packages, either by the version or the version range that you defined, and then pick out, well, what are the CVEs that are attached to these, or are there known exploits in the wild or other vulnerabilities? Really popular one that you all probably know about right now, GitHub's Dependabot. It is just free. It's just available with GitHub. It will open up PRs with suggestions for bumping up package versions for you. Dependency Track is another one that's out there. It also does code scanning and reports based upon vulnerabilities it finds. And Sneak is also another really popular one. But that's just a few of them. As I mentioned, it's a very broad business right now, and there's a lot of tools out there and a lot of solutions. The big thing that all of these can do for you is they can provide gates that prevent deployments if your dependencies include known CVEs and exploits. So this is one thing that we are currently working on, where we actually don't want our deployment to go if our scanning tool identifies that there is a exploit in one of our dependencies. We want to address it then before it has a chance to make it out into the live environment. So the big topic to kind of talk about here is really infrastructure as code. And if you haven't heard about this yet, infrastructure as code is pretty much as it sounds. It's you defining the application in some sort of structured format so that it is repeatable every time that you go to deploy it. And it's removing manual process from your deployments, because anytime that you are touching things and performing manual operations as a part of your deployment, you're introducing failure points into it, and points of where you could digress from what you're actually supposed to do. Like, you could have the best run book in the world, but if you still have somebody going line by line by line, checking off things that they're doing while clicking around in the console, you're going to end up with a bad deployment at some point, which is going to kick off a bunch of remediation, which is where getting into automation is really, how you address those things. You will go faster and more secure if you actually codify the things about your deployment. Provisioning through definition files, it's that layer of automation where you hand it the definition, and then whatever infrastructure as code system it is takes it and then does the same thing every single time. Your improvements can be iterative, and your changes will get applied by the system in a very coherent manner. The biggest ones that you've heard about are going to be Terraform, definitely CloudFormation, because I know that we have a lot of AWS users here. And even in the same vein, Ansible, Chef, and Puppet are also infrastructure as code providers. They just do it a little bit differently than what you might be familiar with Terraform and CloudFormation. The most important part is that your deployment shouldn't rely on somebody hitting the return key on their laptop to then push code out. We want to have that continuous process of, I merge code, my code gets built and tested, and then my code starts deploying after it passes checks and tests. So this slide, there's actually should have been an asterisk on this slide, because once you hit a certain point of maturity, you could test in production. We're not going to talk about that in this session, though. So this is coming from the standpoint that you are not yet there, where you have that level of maturity and confidence in your processes. For most of us, we probably want to have a CI/CD process that has multiple environments, something that's at least one pre-production environment and then your production environment, at least. Pre-production allows you to perform additional live testing and validation without touching customer data or possibly impacting customers before it actually goes out. Your code changes actually go out to the live environment, the production environment. And again, there are actually lots of people out there that do test in production, but their processes have gotten them to the point where they can do that with confidence and they can reliably roll back or pull or turn off changes. So we're going to walk through the common CI/CD pipeline that you would see in my team, from my team here. In this case, this is just a 2-environment pipeline, and I'll touch a little bit on where we differ at the end here. So on the left-hand side, you have a developer, you've got your code, you've made your changes, you are going to run some tests. So, actually, I think I misspoke here. This might have been the pull request point. The way that we do it here is that we have testing that has to pass when we open up a pull request. So I've written my code, I've opened up a pull request to the branch that, is the main branch on the repo, and unit testing is running as well as vulnerability scanning. So in our case, we use GitHub. We've got PyTest to cover all of our code. We have a gate there for ensuring a certain amount of code coverage. It's not the best gate, but it is a gate to ensure that we aren't adding lots of new code without actually ensuring that we have coverage for it. And then our vulnerability scanning. If any of our dependencies listed in this PR have known vulnerabilities, we want this PR to be stopped. So then that way the developer goes back, updates that dependency, ensures the tests pass, and then the PR can continue. So then the merge happens. And for our purposes, once we merge the main, that kicks off the deployment itself. First thing it's going to go is it's going to go to our dev environment. And it's going to be a full live stack of our application, and it's going to be running out there. The moment that deploy completes, we're going to go into another test phase where we're actually going to be, it's not going to be the unit test that we had with our code, with PyTest. It's actually going to be integration tests where we are actually hitting the service and we're ensuring that all of our APIs operate correctly, that the backend is presenting data the way that we expect in between operations. It's going to go through our workflows. There might be performance testing in there. But ideally, though, this has to pass as well. And then once it does, the build that went into dev, that goes into production. Now, we actually might have more environments than this in a lot of our pipelines. Like our dev environment usually will be where all code merges happen and then everything's validated to be working. And then there would be a staging environment in the mix after that is an exact replica of production. It doesn't have customer data in it, but it is functionally an exact replica, like same amount of scaling, same amount of instances, same number of regions because we deployed to AWS. But that is where cross-team integration can happen, and it's guaranteed to be in the same state as production so that we have an environment that we can actually validate against.
All right. The most important part of our journey is the people we meet along the way. If you joined this room, then obviously you have the same kind of thought processes that we are. So we'd like to invite you to join us to talk about some of these different concepts in more depth. And these can be talked about in a bunch of different places. We have posts all the time on Jamf Nation. There are development channels and Mac admins. Of course, you can find stuff on Stack Overflow. And then look at this event for brain dates around this as well. And with that, thank you for listening.